Some study this prism, hoping to catch the beginning of a light wave. It's a strange thought that some of the rays we bask in have taken millions of years to arrive. More, that this light has taken a circuitous route, being bent by forces such as gravity. Now, scientists have begun to unravel the path of light, and in doing so, may be able to develop a clearer map of the universe. To help us draw a picture, we're being joined by Dr. Olivier Dore. He's a member of the U.S. Planck science team at NASA's Jet Propulsion Laboratory in Pasadena, California. Welcome, Dr. Dore.
Well,
So this isn't your research, but it is a field that you've been looking at for years. Let's start with some basic definitions. What is a B mode and how many types are there?
most of the light we see has some kind of direction in related to it. And for example, it's something that you might wear polarized glasses, which is you see that it filters light and it filters, for example, reflections on water or something like that. And then so it means that polarized glasses are one way to pick up one direction among all directions. And what we call B mode is one characteristic, one way to characterize this polarization of light. And there are two types of polarization that you would call. One would be what we call E mode, and the other one would be called a B mode. Their characteristic is basically they have different symmetries, different way to characterize the symmetries that characterize the polarization of light as we measure it. So it's not so much a frequency, it's like the direction we receive it from, and it's the orientation of this direction, this preferred direction of light, that it has to do with that more than the frequency on the intensity.
Okay, so it's how the light ray actually hits our eye or how it hits a surface.
That's right. That's right.
And so there are many types of B modes, and some of them are obviously coming from stars and the light which are emitted from stars. And there's something called a primordial B mode. Primordial, obviously, when we hear that,
right,
meaning ancient, but what is a primordial B mode?
Okay, so there are two types of B mode signal that we expect. One has come from one effect which is called gravitational lensing, which is the distortion of light by matter, and which is the one we measured. And there is another we just measured, which was just measured. And there's another one which is a primordial one, so referring to the origin of the universe, and it was which was emitted very, very early on at the beginning of the universe. So we think that when the universe was about less than a second old, there is a process happen which we call inflation that will naturally create what we call primordial B modes, and that's really what this whole community is going after now.
And so there
it's a signal that will be very interesting to learn something about the origin of the universe, and so that's clearly a goal of cosmologists nowadays.
And so it's actually possible that we might be able to discover some of these primordial B rays which came into existence only seconds after the universe was formed?
That's correct. Yeah, that's really what as you picked this very, very exciting and it's a very unique thing we can do, but it turned out that was actually really what we are trying to achieve here. Yeah, and that's really the goal. And so, for example, the Planck science team right now is really working towards this goal. So the catch here is the fact that we don't know how important or we don't know exactly how strong this signal should be. So we are really kind of shooting in the dark and trying to measure it. And we might be able to see it, and we might not be able to see it according to really how the universe is. And we just don't know because we don't fully understand all the physical theories that are at play at this time of the universe. And so we are really exploring this signal and try to see if we can see it.
Is it possible that this primordial B mode would be something like the Higgs boson particle in that we don't know exactly what it looks like? They may be all around us all the time, and because we haven't quite defined it, we haven't quite recognized it, we don't have the information.
So I think the connection between the B modes and on a Higgs boson is really not obvious, I would say. But on the other hand, you are right in the sense that it's something, this light, this primordial light, and we're talking about on whose polarization we are measuring is really around us all the time as you speak. For example, which is called the cosmic microwave background. So it's really, and as the name said, it's really a background that's really surrounding us. The classic analogy for that is like if you, back in the days when we were using antennas to get TV and not a cable, you would have, if the TV was not tuned properly, you would have this white snow in the background, right? Like you would have this just noise, and so 10% of this noise is actually coming. It's actually coming from this cosmic microwave background signal. So it's actually surrounding us all the time. And so what we are trying to do here is we're trying to measure the polarization, so this some kind of preferred this directional pattern in light from this background radiation.
Now, what's interesting to me about what is being done here is not simply the effort to find this specific ray. It is that the idea that if we find it, we might be able to trace it back and be able to sort of unfurl and unwind the path that it has taken from its origin point. And in doing so, we might be able to really expand our understanding of what the universe is and what it looks like.
That's really the goal, yeah. So it's really, by measurement of signal, we can then confront our theories with this measurement, and really the interpretation of this signal would really lead us to extremely precious and unique insight into the very, very first instant of the universe. Yeah, you got that exactly right. And so on what was achieved in the work you are describing today is measuring. So there are two types of B mode, as I said before. So there's the primordial and the other one. And so what was achieved in this work is to measure the other one. And so it's a very important It's a very important stage in showing that it can be done. And so now really the race is on to detect the primordial one. And there are really tens of experiments all over the world really going after this signal as we speak. So it's really a race in this community. And the first who will detect the signal is going to be which has a huge impact. And it's really an important achievement.
And from what I'm hearing, the discovery of the B-mode is going to be more than just a spectacular topographical tool, but actually something that will be able to tell us about the origin of the universe, about the formation of light, about all the things that maybe it has intersected over time. Will this really change how we define, how we look at, how we understand the universe?
Yes, it's, as you might imagine, any insight that we can have about this very first moment of the universe. This is really, it's extremely valuable, and if you want, because the energy range and the temperature of the universe is so different from anything we can recreate on Earth by our regular technologies, that it's really opening up a new window into the physics of the universe. It's something really, really unique. So it might have a big impact indeed, yes.
And so let's get into the pragmatics of how. How are we looking for this? What tools, what strategies are we employing?
So strategy is really to build telescopes and to build detectors or cameras, if you want, who are very sensitive and sensitive to the particular frequency range of the light we are looking for. So I mentioned microwave before. So basically, you are talking about extremely sensitive instrument that can measure microwave lights or very, very, very precisely. And then you want not only to measure this light, but you also want to measure its polarization, so this famous direction. So we are talking extremely sophisticated technology, and it's really all this field is building prototypes and really, really cutting-edge technology to measure this light. And so on, there are experiments, and then the detectors are put into space on satellites, for example, like the Planck satellite you referred before, and they also go or sometimes they are put they stay on the ground. And for example, the one that are used for this particular measurement that interests you today it's actually at the South Pole, and the interest of going there is that it's actually very dry, so the air is really dry, and so the water in the atmosphere is going to absorb the light we want to measure. So it makes a huge difference to go in a very dry place like the South Pole, and it's also good to go into a high altitude place because there is less atmosphere, so less absorption. And so it turns out that the South Pole is one of the best places in the world to do that. So there are several experiments who use this facility and build telescope instruments there and will operate all year long. And as you can imagine, it's a very challenging environment to work on. But so pretty very extreme. But scientists are fearless, so they go there, and some people will spend the full austral winter there just to look at to run these experiments.
Yeah, I've actually heard that Antarctica and parts of the South Pole are actually one of the most perfect analogs for places like Mars and other for exactly that reason, because of its very arid climate, and it's one of the best places to train, to look, to study what things are like outside of our own planet. So it is also a good place for that same reason for telescopy.
I don't know. I'm really not an expert on living condition on Mars, but it's very true that the South Pole is actually a very. As you can imagine, it's a very climate than what we are used to, and so it has some very specific properties which are really very beneficial for the measurements we are trying to do. Yeah, so you're absolutely right. So, and the only thing better than the South Pole is actually space, right? So you are totally above the atmosphere, and it's as good as you can ever do. The problem is that, of course, to send instruments in space is very complicated, very expensive. So you need rockets, you need to build satellites, you cannot maintain them. So it's really, it's a very, very challenging exercise. We can do it, but we really do it as a last resort. So if we cannot do things from the ground, then we will try to do them in space.
Probably the last question. You mentioned that one of the things that scientists are working very hard to do is to look for the direction, find the direction which this ray is coming from. Does that mean we know where to look or where it should be coming from?
It's not the direction in the sense of where it's coming from. It's just the fact that light, when you look at it, when you look at the sun, or when you look at some light has this direction imprinted on it. So, and it's not and the fact that it's lights are you can see that as a vibration of some electrical field or magnetic field. And this vibration doesn't happen randomly in space. It happens along some direction. And this direction is what we call polarization. And so this is really the direction we are talking about, not so much where it's coming from. Because as a matter of fact, all these radiations or this cosmic microwave background is really coming from everywhere. And it's something which is remarkable. You can look at any part of the sky. You see this light coming to you. So it comes from all over. And there are deep reasons for that, which is really related to the Big Bang and how the universe came to be. But it's actually wherever you look on the sky, you would see this light coming at you. So it really comes from everywhere.
Searching through the prism for the very origin of light in the universe. I'm Andrew Hiller for The Voice of Russia, and I've been joined by Dr. Olivier Dore. He's a member of the U.S. Planck science team at NASA's Jet Propulsion Laboratory in Pasadena, California. Thank you for the insight and for taking us on this trip.
Thank you very much.